Well, hello, everybody. Welcome to the Stats for the Masses webinar for today, the many ways of interpretation. We're going to look at p-values, effect sizes, and confidence intervals. Okay, well, let's go ahead and get started then with our event. I think it's going to maybe take... it might take the whole hour and a half today, but I'm going to try to leave some room at the end for some questions and such that we could go over. So let me go ahead and get started. We'll just do a little introduction and then we'll get going. Okay. So my name is Elaine Eisenbeisz. I'm the owner and principal statistician here at Omega Statistics. So first of all, I want to thank of those of you who took the time to join live today. We had quite a few registrations, but for those of you that showed up live, it's always nice to have some people here listening and asking their questions. Today, I'm going to present a review of p-values, effect sizes, and confidence intervals, just like the title says. And we're going to look at how they're used to make informed decisions in your research. As usual, today is just an overview, but like always, I hope that the information you receive today will give you some ideas and guidance towards further understanding your statistical findings. So, like I say in all of our webinars, use what you learned today and apply it in a holistic way. Look at the big picture, and probably this webinar is probably one of the biggest reasons to look at the big picture. All of these things, all three of these, and some more things too. Nowadays, there's all kinds of different ways people are interpreting their findings. But if you learn about these three, it'll give you a good holistic view on things. So let's go ahead and move our slide down here and get started. For those of you who've been to the webinars before, it's basically the same thing. I'm still doing the same thing. I'm still here. But probably the biggest areas are clinical research, clinical trials, dissertation assistance, and I also have a lot of training programs I do now. So those three areas are probably my biggest ones. But anything a statistician can do, I can do. So if you have any questions, you can always give me a call or email. I'm happy to try to help. Okay. The lecture today, we're going to look at a few things here. We're going to do a brief review of statistical terminology and the scientific method, just to kind of give you an idea of why we even started with the p-values and such. We're going to learn about what p-values can and cannot do, problems encountered when we just use the p-value to drive our studies and our decision making. We're going to do a brief introduction to effect sizes, why they're important. I'm also have a little place here about p-values not being all bad, and they aren't all bad. And confidence interval approach we'll look at the very end. I put some handout in the handout area. But of course, I will send it with a recording, after we get the recording all put together nice and pretty. Also, there's a video that I uploaded. It's a YouTube video, maybe about 15 minutes from Dr. Jeff Cumming, and I have it at the very end of the slides, a link to it, which I think would be a great follow-up after what I show you today to go and watch that. And it'll just kind of cement some things for you. And thanks to Isabella Gemmett for turning me on to that video. I've been using it in my trainings and my lectures now for many years. So thank you for that. Okay, so I guess the first thing we should ask is, do you even really need statistics, right? Do we even need to be testing? Big data nowadays will say no, right? The data is so easy to obtain nowadays. You swipe a card and it gets all kinds of information everywhere you shop, right? Everywhere you go, everybody wants your email, everybody wants your information. It's probably amazing how much information the world has on each of us, okay? But not all data is big, right? Sometimes, like a lot of my times in the clinical trial space, we can't go out and collect data on everybody. Each person maybe costs tens, hundreds of thousands of dollars to treat. So a lot of it is about time and money. So a lot of the work I do, we don't have all the data in the world. Okay. But the main reason that we do need the statistics is to make our best guess of the truth. I do have here a note that, however, statistics doesn't give us the truth. A lot of people will say things like they want to prove something with their statistics. Right off the bat, I'll tell you, statistics doesn't prove anything. We're just very good guessers. If we knew the truth, you wouldn't need a statistician. Okay. But in statistics speak, you're going to hear words like variability, uncertainty, error, noise. They're all words for the same thing. We deal with the variables. Not everybody's the same age. Not everybody has the same response. So it varies person to person. Not like math where 2 plus 2 is 4. In statistics, I always like to joke 2 plus 2 is 4 and maybe a little type of error, because it's not always 2. But you'll hear words like that. And that's really what we're measuring with statistics, is this uncertainty in the data that we collect. And there's reasons for that. Statistics, like I said, are guesses at the truth. We usually don't know the truth. Often in statistics, you'll see problems like in statistics books and such where they'll talk about a true population mean or a population proportion, something with population in it. What we're going to do with statistics is we're going to estimate the population number, whatever that might be, the mean, coefficient, or something like that. We're going to measure that from the population. But the population is the complete total collection of every possible item, person, unit, whatever we're measuring. Okay, it's everything. Well, we can't go out and look at everything. A lot of times, too, at the quality control space where I work in quite a bit, you're looking at a lot of product. Maybe I have an example in one of my events about looking at light bulbs and how long it takes for the light bulb to burn out. Well, you certainly can't go and look at every light bulb in that lot and burn them out. You won't have any light bulbs left, right? So what we do, we have the population, which is everything. We have this parameter that we want to guess at, like that's like your mean, or, so something like the proportion, something like that you're trying to find. But you don't know that, right? Because you're not going to look at everything. So what we have to do that are statistics. We have a sample. The sample is the subset of the population. So maybe we have a huge population, but we'll go out and we'll pool 200 people, or maybe we have that a lot of 100 light bulbs, and maybe we'll pool out 10. That's a small sample, but you don't want to look at a lot of them if you only have a lot of 100. You won't have enough to sell, but that's for a whole other talk where you talk about power analysis and sample size and such. But what we're going to do is pull our sample from the population, okay? And we're going to use the sample to make our good guess. And what we're going to do is take a statistic that we derive from our sample and use that to estimate that parameter that we want to know. We want to know the true mean. We'd love that, but we won't know the exact true mean. So we're going to make a statistic, which should be a good guess. You might also hear it called a point estimate. It's one single number, and that statistic, like I said, estimates the parameter. I do have here a note that we would prefer to have a random sample. It's the best kind of sample, and the reason is because it's going to be representative of the population. If I was to have that lot of 100 light bulbs and I was to pull the first 10 that came off the line, there might be a problem with the first 10 that come off the line. So what I want to do is randomly pull, a set of random numbers out of that 100. So I get a good representation, okay, of the lot. Same thing with other studies. Some studies, though, like in clinical trials, people will be randomized. They'll come from the doctor, they'll be referred from whomever, and what we'll have is a randomization schedule. So as they come in, they're going to be random into one treatment or control or something like that, depending on when they're coming in. So we're still doing randomization. So we really want something like that. A lot of times statistics do not have the randomization and they're still used. But if we can get this random sample, we're happy. We're happier. We have a confidence interval. We'll talk about that at the end today. So, we're getting that guess, that statistic or point estimate of that population parameter, right? But sometimes you're not going to be exact. We're making a guess. We're not going to get the exact true mean. The only way you would do that is to look at everything in a population. So we have a guess. And then what we're going to do is we're going to take that value of our guess and we're going to put a little cushion around it. And that's our confidence interval. So what we'll say, for instance, maybe we'll say, the average burnout time for the light bulb was, 2 years. However, the confidence interval, that would be our point estimate, but the confidence interval might be somewhere between maybe I don't know, 18 months and 26 months or something like that. It's symmetrical, so I didn't think of it in my head. I'm probably off there. But let's say it's 20 months or is our light bulb burnout time, but we have a confidence interval built around it so that we can say we guess 20 months, but we're 95% confident that the true average light bulb burnout time is somewhere between 18 months and 22 months per se, something like that. And that's what we're doing with our statistics. We're deriving all these things to help make our conclusions. Okay, so basically it's a cushion around our estimate because we're never going to be nothing's 100%. So here's a little graphic I made a long time ago, but I thought it would be useful for today. Here's the things we don't know on the left and the things we can find out on the right. So on the left, we have our population. We have our parameter, which is what we want to know. Maybe the average light bulb burnout time, right? And that's the truth. If we had that, that's all we'd need. We won't need our statistics, but in many cases we don't have everything. So we pull a sample, then we derive a statistic, which hopefully is a good guess at that parameter. And that's what it is, a very good guess. We could be wrong. We probably are. So we're going to add that confidence interval as a cushion. Okay. So let's talk a little bit about the scientific method. Statistics is the keeper of the scientific method. Okay. And I take that job very seriously. And we use theory and the tools of statistics to perform our studies according to the scientific method via hypothesis testing. And I'm not going to give you a big, long talk about hypothesis testing today, and it depends on what book you're reading or whose video you're watching. However, I think of it as 5 steps, and a lot of resources do. First, we're going to formulate research questions and our hypotheses to explain something, right? We're going to come up with what our research questions are. Then we're going to specify what our statistical hypotheses are, and that's our null and alternative hypotheses, okay? Then we're going to make a choice of an appropriate test statistic, and that's basically what test are we going to use. We're looking at 2 groups, maybe it's a t-test. We're looking at a regression model, right? Are we looking at more than 2 groups? And it's an ANOVA, things like that. So we have to choose what test we're going to use. Then we're going to run our numbers. And if we're doing some kind of comparison of a mean to some mean we want, or maybe we're looking at 2 means for maybe say male and female or something like that, or more than 2 more than 2 means or something like that. Well, we're going to get a p-value, and it's going to be a probability, okay? And we're also finding what we're finding if there was truly no difference. And I'll go through that in a minute. And then we're also going to build a confidence interval. And then we're going to determine if we have statistically significant results. And then we'll properly state our conclusions and make our inferences based on these test results. I think I'll talk about a little bit later. There is a little bit difference between statistically significant and meaningful significance or clinical significance. Again, some people put too much value into statistics. And remember, they are guesses. They do provide support, but you're never going to know what the truth is. You get a good guess at it. Here's another little diagram. It's a circular process. We have inductive and deductive reasoning in the scientific method, but you observe, you see some patterns, maybe you do a hypothesis, you test it, come up with some kind of theory, or maybe you have some idea or theory, and then you're going to develop your hypotheses, ask your questions. Then you're going to go out and collect your data, make some observations, and you're going to confirm with your statistical test. Then you go out, you'll observe again, okay, and again, maybe some more. So it's circular, around and round and round. One test, one statistical analysis is not going to prove anything. Our body of knowledge using the scientific method is built on this repeated testing over and over again until we get enough body of evidence to really support what we're doing, what we're looking for. Okay, so we have theory and hypotheses. A typical use of the word theory implies a belief based strictly on observation and personal experiences. Like it's a hunch, the sun has been rising every morning all my life, so it's going to come up again tomorrow. That's my theory. However, scientists will use a theory as a conceptual framework to explain not only an observation of the sun rising every morning, but also the mechanisms behind that observation. So in essence, the theory of gravity not only explains why the sun rises each morning, but also the path of the planets around the sun, tidal motion, projectile movement. So, it can explain a lot more with that. Okay, but it has to be testable theory. Okay, and how do we do that? Well, we use hypothesis testing. In everyday usage, you might say something like, I hypothesize that my new rooster is going to crow in the morning when the sun comes up. But to a scientist, it's a working assumption. Okay, so typically what you'll do is you'll devise your hypotheses, and then you'll see if that holds water by testing it against data or information that you collect. Okay, and you'll get all your data, and then you'll run your test, and you'll test your hypothesis. Okay, if the test confirms your hypothesis does hold water, then you're going to I have here, then the scientist declares this hypothesis to be a theory. Like I just said, one analysis and one study will never really develop a theory, right? It usually takes more than one hypothesis test and confirmation to arrive at a generally accepted theory. And this is because we have reproducibility and falsifiability. Okay, that's inherent in the scientific method, and they're very important. And thanks to Karl Popper. Again, we have that circular thinking, remember. But reproducibility, you have to be able to reproduce it so that other researchers can recreate the conditions of the study. So when you do your reporting, you want to include enough information so that another researcher can go out there and run a similar study. Of course, they'll collect different data, but you're hoping that one would hope that another researcher goes out, does the same study with a different sample, and comes up with similar conclusions. Okay, and that's your reproducibility. If somebody can't go out and reproduce it, then it's not really, nobody can check it. And it would be hard to really say that you have anything of substance there. Then there's also falsifiability, and that's inherent in the reproducibility, because a person could go out, reproduce the study. Maybe your study showed you had statistical significance, and it supported your alternative hypothesis because we test the null, and I'll tell you about that a little bit more in a minute. But somebody else will go out and they'll run the same study with a different set of data, and then they'll come out with a different conclusion. They'll find maybe there was no difference. Maybe they didn't have statistical significance. So we never prove anything using the scientific method because of this. These two concepts. Further study could prove us wrong. And Einstein actually said, no amount of experimentation can ever prove me right, and a single experiment can prove me wrong. Okay, so, but again, I don't like the words prove, but hey, Einstein, he can say it if he wants, but it's about the point and not necessarily the wording he used. You never really can prove anything. Again, remember, it's all just guesstimates. We are very adept at being educated guessers, and if we knew the truth, we wouldn't need to do all this work. So that scientific method helps us to do our guessing, and it's actually based in frequentist theory. There's two main schools of statisticians. There's frequentists and Bayesians. They get along a lot better now. About 20 years ago, when I was in graduate school, they didn't get along so well. I actually did have one teacher that frequentists were older and the Bayesians were a little younger, and he was a Bayesian, maybe one of two on the staff, and he used to come into class all frustrated and say that the other statisticians needed to retire because they didn't agree with his approach. Nowadays, Bayesian has become very acceptable, more and more so. I do a little bit of both. What we're looking at today, though, is going to be based mostly on the frequentist, where you have frequentists. The big difference is frequentists assume they know nothing until they go out and they pull that data. Okay. Bayesians, on the other hand, they'll say, well, we know from prior experience, or, from the way this test is, that maybe they have a diagnostic test or something like that. It's used a lot in diagnostic testing. And they have some ideas how good that is, how good their test is, how sensitive it is, the specificity, things like that. So they'll take that information and they'll use that to set up their design of their study. But frequentists don't. We assume we don't know anything until we go out and pull data. Okay, so that's the big difference. And to do this, we use the p-value. So earlier this week, I was sending the reminder email, that we're having the webinar today and it's free, sign up, yay, I actually got an email that afternoon, and it was just from this guy. I'm not going to give his last name, but I don't even know him, but Jason H sent me an email and he said, p-values are bullshit. And that's all he said. He said nothing else. I emailed him back and I said, in a way, you're right. You're kind of right. They are a little bit. Okay, they do kind of fall apart, and I'm going to tell you why. But they're not, I wouldn't say they're total bullshit. But I had to bring that up, and I had to make this slide. So anyway, this is actually a very nice p-value. Usually we like them to be under 0.05. So this would be in many studies statistically significant, but that bull doesn't like it. But I'll show you some reasons why they are this and why they're all not total bullshit. They aren't easy to describe. Okay, first of all, p-values. Even R.A. Fisher, he kind of dreamed them up probably 100 years ago. Yeah, getting close to it. It's difficult to interpret. R.A. Fisher, he was a geneticist and statistician back at the turn, maybe a little after the turn of the century, but he couldn't even explain it. Okay, so he proposed a rather informal system that could be used, but he never could describe it straightforwardly, what it meant from an inferential standpoint, like when you're making your decisions and inferring things from your data. In Fisher's system, the p-value was to be used as a rough numerical guide of the strength of evidence against what we call the null hypothesis. And the null hypothesis, typically you have two hypotheses in your research with the scientific method. The null is the hypothesis of nothing going on here. And that's why it's null, zero. So zero difference between my groups. If you're doing a regression model, none of my that coefficient or none of my coefficients are significant, for the outcome. So it's actually the null hypothesis is what we're testing. Okay. And what the p-value is it's a probability. What it basically is in English, it's the probability of getting what we see with our sample or more extreme results, giving that our null hypothesis is true. So how rare would this finding be? Because it is a probability. Okay. A lot of studies set a p-value at 0.05, and we're just going to go with that today. But the p-value is very arbitrary. You could set it to whatever you want it to. Some studies do set it at 0.01. And that's kind of allowing a 1 in 100 chance that you would see something that you're seeing. But 0.05 is good. That's a 1 in 20 chance. Okay, that you'll see things just by chance. Sometimes the p-value is 0.1. People will do that a lot of times whenever they don't have a large sample. But typically 0.05, and 0.05 is 5%. And what that is saying is that 1 in 20 times, it's allowing me to be wrong, that just by chance, I happen to pull a sample that shows I have a difference when I don't. Because it is possible you go out there and you pull your sample and somehow you get lucky, because it's all based on probability. Okay, so when we use a p-value of 0.05, we're allowing ourselves 5%. So we're allowing ourselves to be wrong 1 in 20 times that we just got lucky. And that's pretty good. Okay, so basically that p-value is just telling us how rare would this finding be if there truly was no difference or there was nothing going on. Okay, and see, it's not that easy to understand. Actually, here's if you want to look at more about it, here's a link to Not Even Scientists Can Easily Explain p-values. And a lot of times when they do explain it, they forget that with repeated testing, right? Because you have the probability, well, that's not about in your sample. What that probability is really representing, that p-value, is that if I was to go out and do this again and pull another sample, what would my probability be of seeing what I'm seeing in what I've done? Okay, so it's a pretty interesting little video to watch or to read. I think there's a video with it too. So I was talking about a little bit, but small p-values are what we'd like to see. The smaller, the better, right? Many studies use what we call a 95% level of significance or significance criterion. You'll see it sometimes as an alpha, and it's usually also 0.05. Okay. This means that we're allowing ourselves to be incorrect in our guesstimates and conclusions, that there is indeed something going on here 5% of the time. Okay. So here's how that's figured out. Okay, that's where I got the 1 in 20. Okay, if we're assuming that we have a 95% level of significance, then we want a p-value less than 0.05 to say that our findings are what we call statistically significant. And that's what a p-value can do. It can be used to provide evidence against that null hypothesis of nothing going on. Okay. So if we have a low p-value, it means that the results we see in our test of nothing going on, since we're always testing that null, are rare. They have a low probability of occurrence. Okay. Jerry wanted to know if using bootstrapping would lower a p-value. Yes, it could, because you're actually putting more info. Would it lower the p-value? I'm thinking more of confidence intervals. Bootstrapping is going to return different p-values probably. The thing is, every time you run a study, you're going to get a different p-value. And I'll show you this in a little bit. And watch that video by Dr. Cumming, and he will show you how p-values jump all over the place, Jerry. Even from with the study to study. Every time you pull different, it's the same study, but you're just pulling different data every time. And the p-values are all over the place. Sometimes you have significance. Sometimes you have no significance. Sometimes your p-value is 0.8. Sometimes it's 0.02. It's weird. So that's where the p-values kind of fall apart. So yes, if you bootstrap, you will probably also get different p-values. Your confidence intervals, though, should get smaller. And we'll look at confidence intervals in a little bit. But see, that's where they fall apart a little bit. That's one of the ways. Okay. Here's some things that a p-value can't do. Okay. I'm not going to run through running a test today. I'll show you some results though. And I have some other videos though. Go to the YouTube channel, and I have like back to basics and such, and I actually go through how to set up a hypothesis and test it. Okay. But let's look at some reasons why p-values are bull, you know. I love that. Although a p-value can give an indication of how rare a result would be, given that there's nothing going on here, shouldn't be anything going on, it can't be used the other way around to say that our alternative hypothesis is true. The alternative is what we want, right? We want there to be a difference, say, between our 2 groups or 3 groups or whatever. We want there to be, but the null is saying that there's not, right? But we can't, if we don't have significance, that there's a difference, we can't turn that around and say, oh, well, then, it must be true. My alternative, must be true. It can be used to support your alternative, but it can never be used to prove it, because statistics never prove anything. Remember, they're just guesses. So you can't even use a p-value to say that the null hypothesis is true. Okay, we don't say anything's true. We don't prove anything. We're trying to guess at the truth, but we can't say our guess is true. Okay. And I have here that there can be any number of things that are contributing to the probability of the test, and a p-value alone is not enough. Again, they never prove anything, statistics. And a p-value may show statistical significance in a study, but that doesn't mean there's clinical significance. And I'm going to show you a little example of that in a minute. But you might say that, a clinically meaningful difference might be maybe a 10% increase in something. Okay. And you might have gotten that 10% increase, but for some reason, maybe your sample wasn't small enough to give you a low p-value. That doesn't all of a sudden throw out that you got a 10% increase. 10% increase would be what your effect size is. That's an effect size. Okay, so you'd still have clinical significance, just not statistical. And you probably might have underpowered the study. If you knew up front what difference you were looking for, you could put that information into some software or some calculations and figure out your sample size. That's a whole other webinar. Go to the YouTube channel. I have one there, and watch it. However, you can have clinical significance, but not statistical support. Or you can have statistical significance, and it could be not mean anything. Okay, and I'll show you an example. Okay, here's some naughty things that researchers do with p-values. We conclude that a significant p-value proves something, right? We change the level of significance to accommodate an almost significant p-value. That happens quite a bit. I have an example here that a test returns a p-value of 0.06. So the researcher changes the level of significance. Maybe they set it at 0.05, like the standard, but they went ahead and changed it. Oh, I'm going to say that my level of significance is now 90%. So I only need a p-value of 0.1 or less, 10% or less, instead of 95. And all of a sudden I have instant significance. Another one I don't like, and this happens a lot, It's actually gets written up in journal articles where they talk about approaching significance or trending towards significance. And so they'll have a p-value set at 0.05, which means you need less, your p-value to be less to say you have statistical significance. But then they do get something like a 0.06 or a 0.09 or something. They'll say, oh, it's trending towards significance. Well, how do you know it's not running away? How do you know it's not trending the other way? You know, it might be trending up to 100%. We don't know. So I don't like that at all. I set the p-value. If you want to be able to say that a p-value of 0.05, or say 0.06, 0.07, something that is significant, set your p-value higher. Set your level of significance higher so that you can say right up front. You can't change it after the fact. Do it before. Okay. Another one is a fishing expedition. People take some data, they run a lot of tests, and they see what comes up significant, right? And then they use those and write those up. Okay. There's something called multiplicity. I don't think I have a webinar on the YouTube channel for it, but I should get that done and posted. What that is, that multiplicity is when you run a lot of tests. Remember, I was talking about type 1 error quite a bit. P-value 0.05 lets you be wrong or just lucky 1 in 20 times. That's for one test. I do 5 tests, then I'm getting lucky a lot more often. I have a lot more probability of getting lucky. If I do 10 tests, even more, to the point where if I do many, many, many tests, just by chance, I'll just get lucky and get a low p-value somewhere. Okay. So don't do that either. Set up whatever you're going to do beforehand, make any adjustments you might need for the multiple testing, and then go from there. And also cherry picking, which is kind of what I was saying. Once you run all these tests and you catch a lot of fish, then you're going to pick the ones you like, right? And then set up your study after the fact. Don't do that. You have to set up your questions and your hypotheses and everything before you go out and collect the data and run your tests. And I talked about this a little bit, but the very large samples, it is the era of big data. It has been for some time. And it makes it very easy to get data, all the softwares that are out there, all these wonderful YouTube videos and such, and these nice webinars that I and others present and such make it very easy to learn about statistics and, to set up your own studies. But so anyone really, can perform, you put a little effort in, a lot of people can perform statistical tests. But they're practically useless when you get very large samples, and it's something called overpowering. And I'm going to show you an example of that. Overpowering is when the sample's so large that you're going to see low p-values everywhere, even on the tiniest little effects, tiniest little differences. And so since that p-value is going to be significant for very large samples due to this overpowering, we need to look at some other measures in the study. And one measure to use would be the effect size. And I'm going to go over that next. I have a couple questions though. Michelle asked if they don't prove anything, then why use? If statistics don't prove anything, well, because they support. They provide support. They don't prove, but they provide support. So that's why we do it. You have a hypothesis, you test it, and it supports your theory or your idea. So that's why we do it. We don't know the truth. We don't know the truth in a lot of things. So that's what statistics helps us guess at that. So they help us to support it. Jerry said p-value equals 0.051. Yes, that would be something where you might say it was trending, right? A lot of times too, it'll have to be, I like a p-value less than 0.05. Some people will say less than or equal to. I suppose you could go either way with it. I like less than. Personally, but I have had people that said no, 0.05, I want to call that significant, and fine. Just set that up beforehand. Make sure when you set up your hypothesis in your study that you're saying less than or equal to. Okay, and let's see. Barbara, can you restate the raising the p-value from the beginning? I'm not sure what that means. Maybe you can ask me at the end, Barbara, on that one. Oh, Jerry has used the term marginally significant. Yes, okay, yes, people will use that. I don't like it, but that doesn't, just because I don't like it, I don't make the laws, and you will see it in papers, but I'm just giving my reasons about why I don't like it. We do enough guessing. I don't want to keep bending it more and more. That's the way I look at it. And I'm conservative. I would rather err on the side of caution. I have, there's a group of people I work with. It's actually quite a bit over the years. They're not the pharmaceuticals, right? They're FDA regulated and such, but they're nutraceuticals and diets and, your energy drinks and things that aren't regulated by the FDA, vitamins, things like that. Oh my gosh, I call them the cowboys because they will do all these things. They love that marginally significant and the trending towards significance and such. And I call them the cowboys. And I don't like to be a cowboy. I like to be a little more conservative. Um, Here's some current happenings regarding p-values. The American Statistical Association back in 2016, so it's been a while now, but you could look this up and it kind of tells you their position on p-values. There's one journal, there's more journals now, but here's one. They no longer accept, they haven't for a while, accepted submissions with the null hypothesis, statistical testing, or p-values. They want things like confidence intervals, effect sizes, things like that. If you send them a paper with p-values in it, they'll send it back. Okay. And many more journals, and dissertation committees, even the FDA. FDA still likes the p-values, of course, but they're asking for a little more information now. They don't want just the p-values typically now, but the estimands, they call them, where you have your research, your hypotheses, but also something called estimands, and then, which are very similar to a hypothesis, but they want to see your effect sizes. They want to know about your power of your study, and they love the confidence intervals and such also. Okay, so it doesn't hurt to include p-values, effect sizes, and confidence intervals in your study, in your findings, in your reporting. Okay, so if you want to learn more about null hypothesis, statistical testing, and our p-values, good and bad, here's a nice, easy read from San Jose State University. It actually has a very fun information in it too. Talks a little bit about Fisher and how he didn't quite even understand himself what he was talking about sometimes, and or at least explaining it. Sometimes too, I think you kind of know what you're thinking, but it's hard to explain. So let's see if we have any more questions for now, and then we'll go into effect sizes. But I'm not going to go through the whole of p-values, effect sizes, or confidence intervals today. I'll try to answer what I can. And those of you who have seen me over the years know that you can always send me an email, and if it's something I can answer quickly or give you a reference for, I'm happy to. If it's something that takes a lot more work, then we can talk about cost, but always happy to help because you guys are my people. So let's look at effect sizes. I have like small, medium, and large, and that's kind of where we'll be at today with it. Again, very simple. I'm not going to go too in depth, but at least you know the words. You can always, Google's your friend, right? I always thought, well, if I had to be a statistician 50 years ago, I'd have to live near like a big, big, big library. Like I have to live in New York or something, because just to be able to go look things up. But now I can look things up on Google and buy journal articles. I can talk to colleagues. It's awesome. I could always talk to colleagues, but okay. So let's look at effect size. Okay. According to Wikipedia, effect size is a measure of the strength of a phenomenon. Okay. So we have the p-value. It'll tell us if the effect is significant, statistically significant, according to probability. But an effect size, the p-value doesn't tell you how big the effect is. It doesn't tell you how. Some people will say, oh, I have highly significant when they have a p-value of, say, 0.001. Don't call it highly significant. You either have significance or you don't. It's like a binary thing. You have it or you don't. Some people, it's kind of like with the marginally or approaching significance. You either have significance or you don't. I don't play around with this stuff. Okay. But that's what the effect size does. So I might get, I have a p-value. I was testing, say, depression scores between a treatment and control group. And, I had statistical significance, right? Oh, yay, my p-value was less than 0.05, but it doesn't tell me how big the difference was, right? That's what the effect size does. Okay. And there's many ways to compute an effect size, more than I can go through today. Practically every test you have, all the different statistical tests will have a different way to compute an effect size. Okay. There are effect size calculators online. There's books with formulas. But there could be, here's some examples of some different effects. You could have a mean difference. So you subtract one mean from the other mean, and that's an effect size. How big was that mean difference? So it would be like for your t-test or your ANOVAs, things like that. Or maybe you have an association between two variables. So you might have a correlation coefficient. Correlation coefficient is actually an effect size because it measures both your magnitude and direction of your relationship between two variables. Okay, so, or a regression, right? We'll have coefficients and such in regression models, and those are related to your effect size. How big's the coefficient? And so these are all different types of effect sizes. Okay, so we could find it by using formulas, and some of them get very convoluted. Cohen's d is a nice, easy one. If you have an independent samples t-test, boom, you're done. You just take the one mean, subtract the other mean, divide it by a standard deviation. Hopefully, it's the same for both groups. Otherwise, you'll have to do some extra little numbers down here. But this is basically taking a pool, or assuming they're the same. Okay, standard deviation. Again, I'm not going to go into it too much, but here's one for an analysis of variance for an effect size. Okay, here we have to sum a lot of things, and we have to take every single mean and subtract another mean from it and square it. And then we have down here how many groups we had, and then we have our variance here of our error. Oh, and then we have to take the square root. Oh, there's a lot of ways you can do it with software. So, check into that before you have to go and do all these things. But sometimes they get a little convoluted, and I do have to do them by hand or in an Excel file with formulas or something. But a lot of times software will give you the effect size nowadays, for the most part. Here's one for correlation. You can see here that gets pretty crazy. You want to learn more about it? You can go and look it up. But I have here that, in fact, the correlation coefficient itself is an effect size. Okay, and we're not going to compute any of them today, but just to know. So how do we find it then? Well, researchers in behavioral and social sciences or working under dissertation will use Cohen's power primer. That was in 1992. Holds up, still good, but he has a whole list in there of all common tests and what different effect sizes are. Okay. Instead of computing formulas, he makes use of these rules of thumb, or a lot of researchers do, and we can give it according to small, medium, and large. So here's Cohen's d. Here's the different values for small, medium, and large. These are just thresholds. Here's Cohen's f. We'll use that for an ANOVA. Here's different effects here, and here's our correlation coefficient. This is small, medium, and large. Okay. So the next question would be, oh my gosh. What exactly is small, medium, and large then, right, for our effects? Well, according to Cohen, small effect is real, but it's difficult to detect because it's rather small. So I have here that it might be the differences in weight between 2-year-olds and 26-month-olds, right? There's only 2 months difference. You're not going to see much of a difference. Okay, so you're going to have a small effect. Medium effect, it's large enough to be visible to the naked eye. So differences in weight, say between 3-year-olds and 5-year-olds. Okay. Or you have some other measurement and you go, oh my gosh, that's a big difference in scores there. Maybe you're looking at depression scores or happiness scores or something, but you visibly can see it, right? And then a large effect is grossly perceptible and therefore large. An example might be differences in weights between first graders and sixth graders. No way are they even close, right? Those are different kind of generalities of some effect sizes. Here's some I'm going to show you an example here. And it's going to have p-values. It's also going to have effect sizes in it. I don't think we have the confidence intervals in here. You know why? This is a chi-square. Confidence intervals are hard to do for, this is called a non-parametric test. So chi-square is non-parametric. It just means you don't need a normal distribution to do it. Today, when I show you confidence intervals, it's going to be for the parametric tests that need that symmetric normal distribution. And that's where they're nice and symmetrical. But the chi-square, you can get effects, you can get confidence intervals for non-parametric, but they're very hard. They're not symmetrical a lot of times. So we won't even look at that today. I'd have to look that up. So anyway, here's an example. Okay, we'll just run through it real quick, and I think it might give you some understanding. Years and years ago, there was a state, this actually was a state of New Jersey, and I did a study where we ran some numbers on seropositivity rates on HIV. Okay. And there was a rapid test that was a new test, and there was an old standard test. Okay. And there were two time periods. The old standard test, it took a while to get your results back, right? Maybe it might take, a week, maybe 2 weeks, something like that. But the rapid test, you could go in, get your test, maybe sit around the doctor's office and get it in a half hour. Okay. So what we wanted to look at was to say, was there a difference in the rate of positive HIV results, seropositivity? Was there a difference in the rate of people that had positive tests using the old versus the rapid test? Okay. So that's what we did. We ran a study. Basically had a total of about 480,000 people in this study. Here's how many people we had in total in this study. We had a very large sample size. And remember I said p-values fall apart. With large sample sizes, you'll see significance on the tiniest little things because you overpowered. You have so much information in there that most tests are statistical tests with the p-value are very sensitive to large sample sizes. And in statistics, when we talk about large sample sizes, we're talking maybe 50 or 100. We're not talking even about 480, but we had this huge sample. Okay. In one group, say we had, in the old group, let's say rapid code 1, these were the people that were in the older group, and these were the rapid testers. So, and even at that, well, maybe it was the other way around because it looks like this one had 371,000. Okay. And then this one had about 108,000. So let's say these, 1 were the rapid test and group 2 were the, ones that had the older test that took a while. Okay. But here's our seropositivity rates in each group. So for the ones that were in a rapid test, 1.7% of the people who took the test tested positive. Okay. In the other group, in the older group, that had the long wait test, 1.8% of the people who took the test had a positive result. That's a difference of 0.1%. That's a tiny little difference, right? It's tiny, tiny. But if you look over here, here's the output of a p-value with the chi-square statistic, 0.004. That's quite low. That's way smaller than 0.05. So that's saying we have statistically significant differences between the groups. However, I look at those two groups and I say, well, 0.1%, really? That's not very big. So is that really meaningfully significant? Is that really clinically significant? So that was a big question, because everybody was so happy that we got this p-value. However, they're the same, right? So what you want to look at is the effect size. So here's Kramer's phi is the effect size for a chi-square statistic. So what you do is you just take the chi-square value and divide it by the sample size and then take the square root. So what basically we take this 8.389 and we divide it by this 480,000 and we take the square root of it and that'll give us the effect size. Okay. So let's see what we did when we did the calculations on it. Here it is. Kramer's phi was 0.004. If you look at Cohen's criteria, or basically you can just look at that and say that's very small. So what it's saying is that, yeah, maybe there was not maybe, but there was a statistical difference. It was statistically significant, but the effect was very small. Okay, so I'm going to report both in my reporting because it's important. You can't just go, oh, hey, yay, I got significance, and then ignore what you really found. Okay. Here's another one with correlations. I have a correlation table. This study was for students, high school students, and peer pressure. And if a student was in sports or performing arts or volunteering, how much did their peers influence them to drink or drink alcohol or smoke marijuana? Okay. So this is correlation matrix if you haven't seen them before. I do have a webinar on correlations. You can go look at that. But you go down here on the diagonal, they're all one because what you do is you go across the row and then you come down the column and it'll tell you what the correlation is. Well, sports, if they were in sports, and here's the same variable sports, of course, they're going to be highly correlated with each other. It's correlational 1. That's why they have the ones. Okay. But remember, if we go back a couple pages here and we look at correlations, 0.1 is considered small, 0.3 is considered medium, and 0.5 is considered large, 0.5 or greater. Okay, so here we go. Let's look at some of these correlations. So we had what 11,718 students in this group here. Okay, let's look down here. Here's one. Okay. So here we had 11,305 people looked at, students, and it was whether they were influenced to drink alcohol and whether they were in performing arts. Okay, so if they were in performing arts, did they have peers influencing to drink alcohol? It's negative, which means that if you were in performing arts, you were less likely to be influenced to drink alcohol, but the correlation coefficient is just 0.079. That's less than 0.1. That's small. I mean, it doesn't, even in Cohen's criteria, that's a weak core. Anything less than 0.1, you might as well be zero. Okay. So in this case, it was not a large effect at all. It was basically close to zero. Correlation to zero means there's one variable doesn't have any association with the other, basically. But look at the p-value. It's 0.000, way less than 0.05. Okay. But again, that's because we have this huge sample size. So you want to make sure that you look at not just the p-values, but look at your effect sizes also. Okay. Then we'll look at some confidence intervals, which will be our next step. So, all right. So I told you why p-values were bull, right? But they're not all bad. Probably one of the biggest reasons is sample size. We need it. The p-value is closely associated with what we call the alpha level or the statistical significance criterion, okay, which is usually set at 0.05 when you need to find your sample size. These are the four things we need to find a sample size. We need our statistical significance criterion. We need power. We need effect size, and we need sample size. Well, if we're finding a sample size, we need these other three things. Power's pretty easy. Most people power their studies for 80%, done. Some 90%, done. Those are typical. Effect size, that's something the researcher or you should know or try to understand. You can get that from literature, in previous testing, things like this. This is the thing that effect size is the hardest thing for a researcher to give me when I'm determining a sample size. They'll go, I just want a low p-value. I want to make sure my p-value is less than 0.05. And I'll go, that's great. What would be a meaningful difference for you? You know, what would be clinically significant? What effect would matter to you clinically? Because we have the power to study for that. And that's the effect size. And they have a hard time telling me a lot of times. So we either have to go back or I have to send them back to look into the literature or do a pilot study, something like that. However, the statistical significance criterion is very closely related to the p-value. As you can see here, the alpha is set at 0.05. So we really need to know what we want. What value do we want? So we can power and pull a big enough sample so that we can make sure our p-values will be less than 0.05. Okay. So we do need to know that significance criterion, which is, they call it alpha and a statistical significance criterion, but whenever you get your p-value, it's going to be the same number. You could set this at 0.1, and then you would hope that your p-value, you want to pull a big enough sample size to be able to see less than 0.1 on your p-value. Okay, so yes, they're not all bad, and I'm sure there's people out there that will argue all day that the p-values are wonderful, the end all be all. However, I think they have very many limitations. They're not altogether bullshit, but the effect size and the confidence interval is going to help. Okay, so let's see if we have some questions here. What about NNT? Number needed to treat. Okay, that was Jerry, and I think I kind of answered it here, right? That's when a p-value is very useful. Okay, or yours, we just changed, call it alpha now, put it in there. What do I want to be able to say is my p-value? And then you're going to do your power. So yeah, hopefully I answered that for you. But yeah, number needed to treat. That's basically how big of a sample size do I need for my treatment group. And then you also need your control group if you have one, and you should. That's a whole other lecture. Maybe I'll do one on randomized controlled trials one time. But so here I have some information here. If you want to learn more about the significance criteria, effect sizes, and sample sizes, look at the power analysis webinar I have. It's on the YouTube channel. I have the link at the end of the slides here for the YouTube channel. There's a link right there if you want to go straight to it. And if you'd like the slides, just send me an email and I'll send them to you. I'm happy to send them to you. Bernard wanted to know, recording or slide be made available? I'm really enjoying the session. Well, thank you, Bernard. Yay. Yes, they will. Here's what I typically do. Just real quickly, we have a little bit of time. I'll do the live event and answer questions, and I love it when people come to live event. And then within a week or so, I will send out the recording of the event, and I'll send out the handouts and probably some announcements of what's upcoming and registration links if you want to come to another webinar or such. And, you know, it's good. I got to do my marketing, right? But yes, everybody here and everybody that registered actually will get slides and a recording. All right, so there are some other approaches to examining data. I'm not going to cover them all today. We will look at the confidence intervals. Prediction intervals are very similar. They're just a little wider, but we'll look at confidence today. You can Google this and see what the difference is, okay? Bayesian methods, I kind of touched on them a little bit. Likelihood ratios, and then there's many more, okay? We won't cover these too much today. I think I have a webinar in Bayesian analysis that you can look at. I have those darn ratios. There's a webinar I have called Those Darn Ratios if you want to look at all the different ratios, which that was actually a very fun webinar too. Going to be covering ratios at the joint statistical meetings in Washington in August too. So I should go back there and look at that video myself. Okay. All right. Let's look at confidence intervals. This is what we're looking at today. Okay. There's a lot of, like I said, there's confidence intervals for non-parametric tests that are very hard to figure out. If you want to know about maybe confidence intervals for the non-parametric test, or maybe for a median or something like, Google it. There's something called Clopper-Pearson, Clopper, Pearson, Pearson. That would be a good place to start. There's R code for them. There's all kinds of things. But today we're going to look at, I'm going to just stick to the confidence interval of a mean, okay, of an average, okay? So basically, remember I said we have that point estimate, and the confidence interval is what we kind of put around it as a cushion. So in this case, what we have is we have a mean. We use X bar, okay? Typically, that's the other thing. Statisticians have 5 ways of showing everything, and it really depends on what we're working at. If I work for social scientists, we write it one way. If I work for clinical trials, I write it another way. If I'm in quality control, I look at this. So you might not see X bar, but it'll be whatever. You know, you just kind of look and see. Always look at the notes and see what the meanings are. But in this case, our X bar is the sample mean. Okay. And then what we're going to do is we're going to figure out this S divided by the square root of n. S is our standard deviation from the sample. And then we're going to divide it by the square root of our sample size. This is actually our standard error, S divided by the square root of n. Okay. And then we're going to multiply it by a Z-score. For 95% confidence interval, the Z-score is 1.96 if you have a two-sided test. Two-sided test means you're just looking for a difference in two means. We'll say two means here. Okay, so we're just looking to see if there's a difference. We don't care if one's bigger than the other necessarily in any direction. We just want to know, is there a difference? Okay, is there a difference between, the treatment and control group? Okay, if we want it to be one-sided, then it won't be 1.96. It'll be 1.64. And I just know these because they're on the top of my head because I use them all the time. But typically, two-sided confidence interval, 1.96 times whatever values you plug in there from your sample. And then you subtract it from your mean, and then you add it to your mean. So I have a slide here, kind of, we'll show you in a bit. And again, we already talked about these, right? Many weaknesses for the p-value. We only can use it with hypothesis testing. It's basically worthless in repeated testing or exploratory analysis because the more tests you do, the more chance you're going to have of seeing a low p-value. You're just going to get lucky. Okay. And type 1 error, that's whenever you're saying you see statistical significance, but it's truly not there. Of course, we don't know the truth, because if we knew the truth, you wouldn't be doing statistics. That used to confuse me. I'd go, well, how do we know the truth? Where do we find the truth? What number's the truth? You're guessing at it, but they'll throw you and say, oh, the true mean is, or the true standard deviation. It's like, where did they find that? Yeah. Usually it's just given to you. Okay. Because if you knew the truth, like I said, okay. And then there's methods that you can use to correct for this where you're saying, oh, you saw significance when there really wasn't, but then you get something called type 2 error. And what that is whenever you're saying you don't seek significance, but it was really there. You missed it. Okay. Again, if you look at the power analysis webinar, I think that'll tell you a little bit more about them. Okay. Also, that p-value we talked about is confounded by the number of observations, right? The more that your sample is, the bigger your sample, the more likely you're going to get a low p-value, okay? Because it's just throwing so much information in there, it's overpowering things. Also, I have here that a statistically insignificant outcome, which means that p-value more than 0.05, that indicates nothing more than that the observed samples may be too small to detect a population effect, right? Or at least that effect that it saw. It's too small to say you have significance on the effect that you got, okay? Altman and Bland said something, and you probably hear this a lot, a statistically insignificant outcome should not be interpreted as absence of evidence. Absence of evidence is not evidence of absence, okay? You can't say that you had a large p-value, it was bigger than 0.05, and therefore my groups are equal. You can't do that. There are tests you can do for equality and inequality. Maybe I'll do a webinar on that. Yeah, that would be good. But this is brought up a lot in that because just because if you have statistical significance, that means yes, statistically you showed that your groups were different. Okay, but if you don't have statistical significance, you can't say your groups aren't different. Okay, you're only testing that null hypothesis of no difference. Okay. Unless you're doing an equivalency test or something like that. But in these are what we looked at today are called tests of superiority, okay, where you want something to be better or worse, or usually better, right? You want them to be different, one thing to be superior to the other. Okay. Again, remember that HIV seropositivity rate, p-value falls apart with those large samples. And sometimes we might not need a p-value. We just want an estimate, right? Maybe I just want to know the mean light bulb burnout time. I don't necessarily need to test it against another lot or against something else. What's the average burnout time, right? For my light bulbs. So why would you need a p-value? You're not comparing anything. You're not testing. Okay. In that case, then you would use a confidence interval. Okay. Because you don't need a p-value. You don't need an effect size, really. You just need the mean, right? But you'll build a confidence interval around that mean because you're guessing, right? And so the p-value is just a number. And again, it gives no indication on the precision of that estimate. You say, I have a mean of 12. Well, how good is that estimate? Confidence interval will give you precision. Okay. And I'll show you. Okay, what do I have here? The big advantage of confidence interval approach is that the intervals give not just an estimate with an associated p-value, but they give an estimate of the range of possibilities. There's that precision I was talking about. Okay, so let's go down and look at it a little bit more. Here's an example. Okay. Different formulas, like I said, for computing confidence intervals, but the one we're looking at today was the one I showed you, where you take the mean and then you subtract z times the standard error and you add z times your standard error. Okay, so here's our little formula again. Okay, so X bar is our sample mean, our standard deviation's up here. Sometimes you'll see an S. Here we have the sigma. Okay, and the z would be the z alpha halves here would be that 1.96 because it's a two-sided test. That's how I know. Okay, and then let's see what we have. We have a sample size up here of 35. Okay, so we had our sample size of 35, and then we had an estimated mean of 15.6 inches. I don't know what it was. Maybe it's a Barbie doll. I don't know. And known standard deviation on the Barbie doll was 2.3 inches. Okay. So I'm going to use a 95% confidence level of significance. That's at alpha of 0.05, which is going to be very similar to saying I want a p-value of less than 0.05. Okay. So I'm just going to plug it in. So here's my 15.6 was the average Barbie doll height, and plus or minus, here's where we're building our cushion. So I take that, compute it, I come up with 0.8 inches. So I add it and subtract it to this 15.6, and now I have my interval. So I have 15.6 as my guess, but I could be 95% confident that the true Barbie doll average height is somewhere between 14.8 inches and 16.4 inches. So that's nice. I mean, that's pretty precise. Okay. As you can see here, the standard error that you use to compute that confidence interval has sample size in it. The bigger your sample size in this denominator, the smaller this is going to be, and the smaller your interval is going to be. So if you have larger sample sizes, your intervals will get wider. Okay. Also, if you are looking for, say, instead of a 0.05, maybe you want a significance criteria of 0.01, that's going to change the z value, which is also going to make your confidence interval much wider. So if your p-values if you're looking at 0.01 for your p-value, expect a very large confidence interval. This is another reason why people like that p of 0.05. I call it Goldilocks. Not too much, not too little. You don't want to pull a huge sample if you don't have to. And if you can, it's time and money. Everything is just about, isn't it? Okay, so any questions on how to compute the confidence interval? Is the point estimate always assumed to be the exact middle of the confidence interval? That's a very good question, Jerry. It's the middle when you're doing the tests that rely on a normal distribution, because a normal distribution itself is symmetrical. Here's our normal distribution. Okay, we've got our little data in here. Here's our X bar, which is our mean in the center, hopefully, if it's truly normal. Your mean, your median, which is the true center, 50 above, 50% below, and your mode, which is where most of your data is, should be right in the center of a normal distribution. So if you have a t-test, if you have ANOVAs, if you have a linear regression model, anything that needs that linear relationship, or this normal makes use of the normal distribution, then yes, you'll have symmetrical confidence intervals equally above and below the mean. Otherwise, no. Akyuta asked, can we use confidence intervals to estimate individual outcomes? Or is confidence interval always used for mean estimates? It's not always used for mean estimates. You could use a confidence interval will go around any parameter that you estimate. You could probably find a confidence interval to go around it. Okay. Individual outcomes. Yeah, if you're for example, like the mean light bulb burnout time. Yeah, you go, okay, here's the sample I pulled, here's the average I got, and I built this confidence interval around it. So yes, you could do that. So yes, they will be symmetrical if you have this normal distribution. Okay, and that's what we're looking at today. I've been doing statistics for 30 years. I'm still learning things, so it's hard to show you guys everything in an hour and a half. I do my best. Here's some nice little graphics I found. I found them from Ransdam, actually. Absence of evidence is not evidence of absence, right? Oh no, that was Blandon Altman. Ransdam, he's the falsifiability person. Anyway, let's look at this here. Here we have confidence intervals for tests of superiority, okay, where you want one mean to be better than the other or something, right? You're testing maybe, treatment control, okay, groups. 0 is here. That's no difference, right? So here's our line of no difference, okay? Up here is where we're saying if we have anything up here in our confidence interval, if we have up here, then we're going to have clinically significant effects if it's from this line up, okay? In here is kind of like might be statistically significant, but not really clinically meaningful. Okay, this is kind of like that example I showed with the seropositivity rates, right? And then down here we have the reverse effect, right? It might even go significant, but it's not what we really want. We want something up here. But in this study, we don't always want this, but for this example, okay? So here's our confidence intervals, okay? So here's our lower bound and our upper bound, okay? And then in the middle here would be our probably our point estimate if we're doing the symmetrical normal distribution, right? So our point estimates would be in here. But these are our confidence interval bounds. So up here in this one, we have a p-value that's less than 0.05 because, right, it didn't cross the line of no difference, okay? That's the other thing. If you have statistically significant findings for a mean, 0 will not be in a confidence interval. If you have statistical non-significance, it's greater than 0.05 for a mean, then 0 will be, if you're comparing two means, then 0 will be in a confidence interval. So in this case, 0 wasn't in our confidence interval. It's way up here. In fact, it's way up here. It's statistically and clinically significant. So we're so happy here. Okay. The next one down, the second one down, we have statistically, but not necessarily clinically significant, because we're not going over the 0. So there is a difference. There's a statistical difference between our treatment controls, say. However, we also, it could be, what if our truth was here? What if it truly was here? Because this means we're 95% confident that the true means somewhere inside this interval. Well, what if it was here? Then we would still have significance statistically, but not clinically. Okay. But if it was up here, then we would still be happy. But since we have no idea of knowing what the truth is, we have to kind of look at the confidence interval. And here we would report, yes, we had statistically significant, but the confidence interval that could be possible that we did not have our clinically significant effect. Okay. Here it's inconclusive. It's non-significant, which means the p-value would be more than 0.05 because we cross the 0, right? So right here, right there, since it crosses over, that means there could be, in this 95% confidence interval, there could be no difference. Our difference could be 0. Okay. It also is up here. If it happened to be up here, we'd be happy. But our interval's covering all of this, so we're inconclusive. Okay. Down here, we have neither statistically nor clinically significant effects. We don't go into clinical significance at all. Our confidence interval ends here. Crosses the 0, so it's non-significant. Okay. Actually could have a reverse effect, but since it had 0, we don't have statistical significance. And down here, this is something, oh my gosh, it's like, well, maybe I was way off with my hypothesis. I didn't even think it out. Or maybe you pulled a sample that was just strange. That's why you need to repeated testing, right? But in this case, we had statistical significance because we didn't cross the 0, right? But we're showing that the other way was better. It's a reversed effect. And because we want a clinically significant up here, and nope, it was here. So our mean difference might have went the other way. Okay, so they're also awesome when you have confidence intervals for these equivalence and non-inferiority trials. Okay. I'll just kind of read through this a little bit. Confidence interval limits are important criteria in the evaluation of relative treatment effects in equivalence and non-inferiority. That's where you have, you're not looking for superiority of one thing over another. You're just looking, maybe they're equivalent, okay, or just non-inferior. So that would be trial designs used for testing if a new drug is at least as good as an old. That would be one example. And the reasons for preferring a new drug could be fewer side effects, lower costs, less time intensive. Maybe it's less invasive. Maybe you have a drug and the standard is surgery, and you are going to look at maybe healing times or recovery times or something like that, or cure rates or something. Wouldn't it be nicer to take a pill, right, than it would be to go and have surgery? So there could be things like that maybe you don't really necessarily need your drug to be superior to surgery, but just equivalent, or no worse than. Okay. That would be non-inferiority would be no worse than. Equivalence would be equal. Okay. And so this margin of non-inferiority, or the margin of equivalence, that is going to introduce that notion of significance into the comparisons. So it's not sufficient to show statistical insignificance with just an estimate and a p-value. Again, that absence of evidence, not evidence of absence. So, and when you're using the equivalency and non-inferiority, it's necessary to show clinical insignificance with a confidence interval narrow enough to exclude clinically significant effects. Okay. All right. So now we're looking at this margin. Okay. This is a margin of non-inferiority or equivalence, depending on what test you're doing. Okay. Here's 0. Okay. If we look up again, here's our dotted lines. If we look up in this area, it's basically saying that our new agent is better. We're looking down here, our standard or our control is better. Okay. So here's our confidence interval. Up here, it actually shows superiority. Okay. But, certainly it's way outside of our equivalence margin. So it's basically showing a superiority here on our confidence interval. Here's another interval. It would show that we have superiority still, but less strongly because we didn't cross that 0. Okay. And we're inside our equivalence, but we also have some superiority. Okay. Here we have no superiority shown, and no non-inferiority is also not shown. Okay. Here we have superiority not shown and non-inferiority was shown. Okay, so down here, it didn't cross this line. Okay, so we do still have maybe some superiority up here. And then we're mostly in here, and we're inside a margin now. So if we're inside a margin, that's what we care about. Okay, and here we have equivalence. It's inside our margin. Okay, no superiority, just equivalence. So this is saying our two treatments are equivalent. Okay. These ones are a little bit harder to understand because we're used to looking at, hey, we want statistical significance on superiority, right? So when you start getting into these non-inferiority and equivalence trials, they get a little bit turned around. Equivalence, if you do an equivalence trial, that's it. You're either equivalent or not. Nice thing about doing a non-inferiority is if you find out that your new treatment or your new agent is non-inferior, then you can go to a superiority trial. You can then go, well, it's non-inferior to the standard. I wonder if it's superior. And you can do that with a non-inferiority. So some people will do that. Okay. And the last thing I want to show you here, I'm not going to show it to you today because I'd rather take the time to answer some questions, but it is about a 15-minute or so video called Dance of the P-Values. Again, thanks to my colleague Isabella Gemmett for turning me on to this years ago. You go right here. He actually wrote a book called The New Statistics, and he's Australian. Australians make the best statisticians. Like I'm pretty good. You know, I'm pretty proud of myself. And we have some great ones in America. We have great statisticians everywhere. But something about the Aussies, man, they make it so easy to understand. And I think if you watch this video, he'll show you also where p-values break down and why confidence intervals are so much better. He doesn't really talk about effect sizes too much. But yeah. Look at this video, and you'll be so happy you did. Okay. Before I go to Q&A, I just want to let you know that we have some news and events. We have the Stats for the Masses grab bag. It's a kind of weekly newsletter. I try to do it weekly, but I get busy. And so usually what it is, the grab bags, it's like things I find during my research during the week, or maybe a project I'm working on and I think it might be interesting to you. It usually comes out on a Saturday, and just kind of like links, or maybe I write a blog post, or it also has all the events that are coming up and things that you can register for. But it's nice. People really like it. And that's why I call it a grab bag, because I never know what I'm doing week to week that might be interesting. That's one thing I like about being in private practice, is every time that phone rings, it could be something different, and I love it. And then I also have the free quarterly webinars, which is what you're doing right now. I haven't decided on the next webinar what it will be, but I will by the time I send out the follow-up with the slides and the recording. And then I'll send a link so you can register also. Okay. And then I have the Stats and Snacks virtual office hour. And that's on the second and fourth Friday of the month, noon to 1 Pacific time. I have one coming up next Friday, and sometimes I call it Stats and Snacks is because I have, I talk a little bit. So I'll give like a little 10, 15-minute presentation. But when you register, you can ask a question, or you can come to the event and ask a question. I maybe do a little presentation just so we have something to do, share a snack recipe, which is fun. I think last week we did mocktails. We had a mermaid mocktail, which is really good. I think next week I'll do plums because they're in season. Anyway, fun. But this is great, and it's free. I mean, you can spend $150, $200 an hour for my time, where you can come to these, ask a question. If it's something that I can answer fairly easily, of course I will. Maybe handouts, things like that. But you can go here to register. You've automatically been added to the list for the grab bag, and so you'll get information on that. But if you want to be in the Stats and Snacks, I was thinking I could register you all for it, but I'll let you go and register yourself. Okay. And then we have the YouTube channel right here. Lots of videos. Go look at that. And I finally offer the fee-based seminars, webinars, custom training. You can go here and look. You can also, if you need a specialized training, ask me. Email me, we'll talk, we'll figure out a price, whatever. Okay. We'll figure that all out. And then here's my contact information. I have here, call me. It's probably better to email. I'm usually quite busy, and I do have an answering service. They'll get the message to me, but send me an email. Okay. It'd probably be the best way. And then I think we're ready for some Q&A. So if we have any questions, yes, Jerry wanted to know if we could submit suggestions for webinars. I would love for you to submit suggestions for webinars. Please let me know. Because I do this for you, so what do you want to know? Right. So definitely let me know. Happy to do my best. And sometimes you might ask me to do something I need to know more about too, which I love. Okay. Eunice isn't here, but asked, without any prevalence value or previous studies, how can we find sample size in a large population? Yeah, that's very hard. If you don't have any kind of thing to fall back on and have any idea of what an effect might be, then you need to go and look through the literature. Okay, look for similar studies. You might need to do a pilot study. Another thing you might want to do is, if there is literature out there, do something called a meta-analysis or a systematic review, where you kind of combine everything that you can find and try to find a pooled effect size. I actually have a webinar on meta-analysis. It sounds like I have a webinar on everything. I don't, but but that's what you need to do. Yeah, sometimes that's the hardest thing, is to find out what the effect size is going to be. Michelle wanted to know, should I use MaxQDA, MaxQDA for data analysis? Michelle, I think that's a qualitative, if I'm right, MaxQDA. You can use whatever you want for data analysis. There's so many softwares out there. Maybe not one that maybe your uncle made, but if there's something out there, R is a great software. It's free. And yes, a long time ago, or a few years ago, people used to not trust it so much. They thought, oh, well, people are all contributing to it. It's open source. It could be wrong, but you can validate it. And there's a lot of things in our software it's a wonderful software. I use it in clinical trials. As long as you validate the routines, you're fine. I like SPSS. It's easy, user-friendly. However, they nickel and dime you for a lot. I shouldn't probably say that because it's going to be recorded. SAS. Everybody knows the price of SAS. I won't talk about that, but yeah, R is great. That's a good thing to start. It has a lot of code, but you can look things up online. You can look up the code online and just play with it and learn it. That's it. If I can't find something in one of the softwares I'm using, and I have probably about 20 of them I use, I can always find something or write it in R. I can write a program. Okay. Then I have here, Martin asked, how do I interpret p-values for a categorical variable in a model where only one category is significant and the rest are not? Post hoc analysis. I would probably look up tester proportion or chi-square test, and you can actually go in and there are some, it's called post hoc analysis that you can do for that. Okay, so that's what you would do is, and the same thing, like if you have an ANOVA and it's not categorical, it's continuous. If you have an ANOVA, you're going to have 3 or more groups. An ANOVA will just tell you if the 3 groups are different, but it won't tell you which ones. Okay. Another thing you might want to do for the categorical variables, if you have a chi-square tester, you can use something called standardized residuals. And anything that's more than a 2 or a 3 usually means that cell in your cross tabulation table is contributing more than the others. Okay. So yeah, look those things up, and that should be useful. And finally, I have here Phyllis, can results of non-parametric tests be used to help explain why significant results are not meaningful, a small effect size? I would say you might be getting into the multiplicity thing. If you have a parametric test and your data is good for a parametric test, all the assumptions are met, use it, because you need less of a sample size typically than when you have a non-parametric test. Some people will do something called sensitivity analysis. And typically, though, that's the other way around, where you do a non-parametric test and then you also do a parametric test. Maybe you would do a t-test and then do a Mann-Whitney U-test just to see if you get the same results or similar, right? So yes, you could do that. That's a sensitivity analysis. So that's possible. Okay. And how do I select sample size when powering a trial? Too much to cover today, but go ahead and look at my webinar. Oh, Jerry said Jamovi is a good free SPSS-like software. Yes, that's very good also. So thank you, Jerry, for that. Barbara asked, I need to understand setting the p-value at the onset of the study and do not make a change after the fact, dealing with fishing expedition and cherry-picking slide. Yeah, definitely you want to do that, because it's cheating, more or less. I mean, well, literally, because what you would do is if you're going to run a test and you're going to pull a sample, crunch your numbers, run some tests, then see what your p-value is and go, oh, my p-value's, 0.2. Whoa, oh, well, I want to, I meant that to be that, that's significant to me. No, you have to do it beforehand. So you need to power your study and set your p-value before. Okay, so you set your p-value, which is going to be strongly related to that statistical significance criterion. You're going to use that to make sure you pull an adequate sample size. Okay. And you're going to use that with your effect size too. So yeah, so you can't really do that. Yeah, your p-value needs to be chosen before you even, as you set up your hypotheses, before you crunch your numbers. Hi.
Hi. So my question is on the where we use the confidence intervals. We always use it for estimation of means, or can we use it for individual, like, the data points?
Yeah, you can use it for, well, you wouldn't put a confidence interval around an actual data point. Like if you say, like you had somebody's age or something like that, you wouldn't put a confidence, because their age is their age, right? So every person will have their data point, right? However, the confidence intervals, whenever you're taking a measurement of some kind of statistic, like an average or coefficient in a regression, something like that, or correlation coefficients, you're going to make an estimate of some kind of statistic, and the confidence interval goes around the statistic, but you wouldn't put them around an actual measurement for a person. Does that help?
Yeah. So I guess, like, I think that my question is that then, so let us say I had a data set, and based on that, I have a mean and everything. So if I do any experiment, right? So how do I predict, like, what would be the value that I would get from the individual experiment? Not like I ran like 10 times or 15 times, where I can predict the average of those 15 times.
Oh, you mean like a Bootstrap confidence interval?
Yeah, so I was just, so the reason why I'm asking is that, so recently we had some kind of, like, we did some experiments, and based on the data, we said that, well, this is a kind of the confidence interval for this parameter, but that's the mean, right? So if I do a next experiment, can I say that the individual value I'm going to get from the same experiment by repeating it, that it's going to fall within the confidence interval, or I have to use the prediction intervals?
Yeah, typically it should fall inside the confidence interval, but you wouldn't know for sure, because that confidence interval is dependent on your sample size, and it's dependent on your sample you pulled, right? So your confidence intervals are always going to be they're never going to be exact, but experiment to experiment, they should hold up pretty well. And if you look at that Dance of the P-Values video, watch that, and you'll see he'll show you these experiments get ran over and over and over and over again, but the p-values jump all over the place. But that confidence interval, it moves a little, but over time you can get a pretty good idea of where your true value would be. 95% sure. Okay, well, you can always email me. You have the slides, you have my information. So if maybe I do that. I do my best thinking in the bathtub. I'll just be relaxed. I'll sit in the tub, and then I kind of have to keep a pad and paper there because that's what I think. So I know sometimes you get away from something and you go, I wonder. So feel free to email me. And like I said, if I have a resource or something, definitely happy to send it or just let you know what I think. But yes, thank you all for attending. And I had a great time today. I hope you guys learned a lot, and have a great rest of the week. And okay, we'll talk soon. Alrighty, bye.